Welcome, OChem 1. I love it. Welcome to Unit 4. Oh my gosh, it's one of my favorites. So grab your colored pencils and your scratch paper. Let's take some notes. We're starting a whole new unit. This unit, we're going to expand our definition of what we were looking at for nucleophiles and electrophiles. It's going to be pretty fun. So let's take a minute and let's just kind of revamp how we started looking at nucleophiles and even bases. You know, we looked for a couple different things. One was a clear indicator right away. Anytime we could find available electrons right away. That is what we're looking at for a nucleophile or for a base. And we started with the easiest ones to find, and those were the bases, and those were straight up negative. So let's take a look at something like sodium hydroxide. Look at that. You've got that clear negative that almost needs a sparkle pen. That was so easy to see. They are just out there and available electrons. Okay, then we worked our way into just a little bit wimpier. Let's say something like water. Well, we've got available electrons. Not quite as available. That nice negative out there just screams nucleophile or base. Our water with that lone pair available electrons, we saw those in our SN1s and our E1s. And now we're going to expand this definition a little bit more. So let's take a minute to actually look at one of our functional groups that we just made in the last unit, and that is an alkene. So let's get a little bit deep here with an alkene. All right, we draw an alkene with all of our sp3s. And then hang on a second, how do you actually form that double bond? Oh, that's a god-awful drawing. Hang on. When we form that double bond, doesn't our hybridization change to sp2? It does. So let's think about that for a second. Let's actually color code. Those hybridized electrons are the ones that are in that single bond holding everything together. So let's think about where the sp3 and sp2 come from. With an sp3, we're using all four of those orbitals, the s, the p, and p. With an sp2, we're only using s, p, and p. So that means we actually have a p orbital out there unhybridized. All right, why do we give a crap? Who cares? Aren't we done with all of that? We memorized our little sheet in Gen Chem and we moved on. No, what that means, space-wise, if we think about our sp2, remember that is something that is nice and flat. So our sp2 part of that bond, nice and flat. And then if we look at that extra p, our p orbitals were the x, y, and z axis. So actually the double bond is not a part of that whole plane. It is not a part of that sp2. Let me put in the double bond, but let's color code those electrons. It is literally out and available. Ah, there it is. We just made that connection. So what's happening is you have a nice flat alkene, but up here and here are the actual bond, alkene bond electrons. They are the unhybridized, and they are literally a 90-degree angle here. They are completely perpendicular to that bond. And what does that make them? That makes them out there and available. So you see where I'm headed. I'm headed back to my list for nucleophiles. Let's think about that. Our nucleophile can now include an alkene. Those are out there and available electrons. So we're taking what we've already learned in our acid-base section in Unit 2, and then we expanded it again in Unit 3, and we looked at things like water, ammonia, ethanol, methanol, things with a lone pair. Well, let's expand it again in Unit 4, and let's look at alkenes. So we made alkenes in Unit 3. We're going to turn around and use them in Unit 4. It's going to be fun. All right, let me pause. I want to clear up some space here. Let me erase. So now when we look at this reaction that I've kind of typed here already, we have a whole new perspective on that alkene. Now, when we look at it, we just see these two glaring electrons right there, out there and available. So what does that mean? That means that if you've got something pretty strong as a partner, what do I mean by that? Well, what reacts really fast with nucleophiles and bases? Electrophiles and acids. So we're going to have that same partnership. And what are we looking for in an acid? We've got that empty shell of an H+. What makes a good electrophile? Some kind of alkyl halide's got a nice long bond and a partial positive on that carbon. So we're looking at those partial positives or full positives. We saw in our last unit with the SN1s and E1s a full carbocation. All of those are awesome electrophiles and acids. So if you partner an electrophile acid or a nucleophile and a base, you're looking at one of the fastest reactions known in nature. So let's take a look at this new reaction we've got here. We've got available electrons right here. I'm going to just mark that as a nucleophile. And then we've got HBr. Well, we know that already from Gen Chem. That is a very strong acid. And it is strong. It's not just an acid, it is strong. And then what in the Sam heck is DCM? Well, our DCM is something that is on our solvents list. That stands for dichloromethane. Sometimes also called methylene chloride. That should be on your solvents list. All right, so let's react it. What do we do with it? Let me draw a mechanism. I've already kind of given it away for free. You see the product, but let's draw the mechanism. It's going to be so much fun. This mechanism is fun. All right, let's draw some brackets here. All right, we've got a nice alkene out there and available electrons. We've got a strong acid, HBr. That's our first step. Right away, that's physics. You've got your electrons. Remember the rule we've been following since Unit 2. We go from where we have electrons to where we don't. We've got this extremely partial positive on that hydrogen. So we're going right here. It's a nice SN2 reaction. Okay, now hold your seats. This is the super fun part about an alkene reaction is that, wait a second, those electrons were actually a part of a bond between two carbons, not just one. So we are going to look at it. Our double bonds literally can swing both ways. So if we are taking those electrons and we're picturing how that bond can form, let me just color code for a second. It's not part of our mechanism, so don't draw this in on your mechanism, but let's picture it's kind of like a gate. It can swing out this way, or it can swing out this way, kind of like a nice Texas ranch gate. You can swing both ways. So let me draw both of them. I always like to draw both of them. Let's call it choices, and then we're going to see which one is the best one. All right, so our gate can swing out this way. So let's draw the product of that. It can swing out and form that bond to hydrogen right there. All right, son of a motherless goat. Well, then what happens to this carbon left behind? We saw that in our last unit. You just stripped electrons away from that carbon. That is a carbocation. Oh my gosh, I wonder if these rearrange. It's like a cliffhanger. Okay, so let's draw the other one. What if we swing the other way? So let's draw that one. We're going to swing up this way, form that bond to hydrogen. And now where is our carbocation left behind? Out here. All right, now we pause for a minute. Now you already know the answer. The answer is in your heart. You already know it. You know it from our last unit with our SN1E1 section. Which one of these transition states is going to win? Which one has the better carbocation? Primary or secondary? Absolutely secondary. That gets a sparkle pen. Okay. So in other words, in Mother Nature, when you do this reaction, that bottom one isn't going to form at all. We have two choices in our alkene, but actually we only form one of them. This is called regioselectivity. You've got two choices, but you end up with only one of them. Okay, now let's figure out what fills in that space. What is going to fill in your carbocation? What do we actually have in solution? Well, we lost a bromine. That's a good leaving group. We lost a bromine. Our dichloromethane is our solvent, or more alkene. The only thing we've got floating around that's going to fill in that space is actually our leaving group, that bromine. So what is our product going to be? Well, we formed a bond. Oh, not good planning. I got to cross lines here. We formed a bond to our hydrogen out here, and we just formed a bond to our bromine right there. So out of this whole process, even though you had two choices, this is the one that you actually made. And this is the one that ends up being your product. So what do we call these reactions? What do we call them? Well, you actually just added to an alkene. Your alkene was your nucleophile. So these are often called addition reactions or alkene addition reactions. And if you look at it, you literally added H and Br to where you used to have an alkene. That is your addition reaction. Now these are a nice combination. You kind of had a second order process here, nice collision, right? But then we also formed a carbocation in between. So it's almost like it's a mixture of what we learned in our last unit. Isn't that fun? All right, let's try another one. Now I'm going to keep these videos kind of short because I've had trouble saving them. So I want to do one more example of this, and then I'm going to end, and then I'll post another video. So let's scroll down. I will always start with some sort of generic alkene. I tend to start with propene. It just shows us where things end up. And then I like to show any kind of stereochemistry. So I'll typically show then a cyclo. And as we go through these reactions, you'll notice I use the same two starting materials, propene and cyclohexene. And with those cyclohexenes, I throw a methyl on there for funsies, just so we can see at the end what our stereochemistry is. And for this one, we're going to add our bromine. And look at that fun squiggle line. That doesn't mean anything. It was just pretty. No, I'm just kidding. That actually means that this will be completely racemic. So what that squiggle line means is that it can be both up and down, 50-50, or bold, or dash 50-50. That is completely racemic. So sometimes that's a shortcut with that squiggle line. All right, so let's look at our mechanism again. Let's do the same thing. We have an alkene. Let's spot it. We have a very strong acid, and we have our solvent. Let's kind of label here. We've got a nice strong acid. This is our solvent, and then this is our nucleophile. Okay, let's start our mechanism. Our mechanisms for alkene additions will always be the same, just like our SN2 and our SN1 and our E2 and our E1. Our mechanism is how that reaction happens, so we're going to start the same way every time. Find your alkene. Find your alkene. That is your available electrons. Where's it going to go? It's going to go to that strong acid, always. First step. We go from where we have electrons to where we don't. Okay? And then this is my favorite part, because alkenes always swing both ways. So I like to show both. All right, we have choices. We could tell by the last example, if you can spot your better carbocation, you always know which choice is going to win. So let's draw both choices. Let's swing both ways. So let's swing out this way. Okay, now remember my green arrows aren't part of the mechanism. I'm just trying to show because I'm not in class, so I can't Vanna White this thing. So let's show our double bond swinging down and form that bond to hydrogen. And then where do we leave behind our carbocation? On that one. Oh, what kind of carbocation is that? Tertiary. I feel a winner already. Let's compare the other one. All right, let's swing. This time, let's swing up that way for our bond. So that means we're going to form the bond here to hydrogen and leave our carbocation right there. Okay. Ooh, how fun. All right, what kind of carbocation is that? That is secondary. So already clear winner right there, tertiary. Tertiary is going to win. All right, if you need a little refresh on your carbocations, remember the most substituted, the most wins. I just made that up. Okay, so out of this one then, what is left in solution? Right now, the only thing floating around that can fill in that space was our bromine that left. Has those extra electrons, it can fill right in. Okay, now this is the fun part. This is why this reaction is racemic. We went from that double bond to a carbocation. That is still sp2. You only have 3 things on that carbon. It is flat. That means that bromine minus can fill in that space, that carbocation, 50-50 top or bottom. It will end up 50-50. It is flat like a pancake. There is no way to have selectivity there. You will only fill in even top and bottom. So what does that mean in theory? That means we can have bromine come in on the top and that methyl ends up on the bottom. That is one answer. That is one part of our 50-50. Or we can have that bromine come in on the bottom. We will be making an equal mixture of both of these. So we will have 50-50 of that. Awesome. So we still have regioselectivity because we ended up adding that bromine on only one carbon of the double bond, not both. So that is regioselective, but it is not stereoselective. We have a racemic product, 50-50. Okay, so let's end this one. And then I'm going to go ahead and put this one up online. Let's see if it's working, and I'm going to go do another one.